Hello and welcome to using ABB Energy Tools. Today we are going to cover how to demonstrate the potential savings to customers using drives and motors. So a quick introduction. So I'm the presenter today. My name is Scott Birchall. I'm the HVACR Global Region Application Engineer for Europe.
So let's look at the agenda for today. So first item is why would you use a drive to control a motor? So the basics of why drives save energy when applied to a motor. What are the potential opportunities on site? So looking at what the potential opportunities look like and what type of setups are we currently seeing. How to use the ABB EnergySave calculator, pretty self-explanatory, so we're going to go through that and the benefits of what you can get out of it. EcoDesign directive, we've got a quick slide on that to cover how it's applied in Europe and the different changes that have happened over the years and how it can help in driving the energy conversation. How to use the ABB EcoDesign tool. So this is another ABB tool where we can look at different things like system efficiency alongside drive and motor efficiency individually. We're also going to look at the power drive system package comparison from that tool that we're going to look at as well. So that should be something that will give a good insight into why there's benefit, and then just a summary to cover all points.
So why do we use a drive to control a motor? Let's look at the reasoning.
So the first item to look at why would you use a drive to control a motor is the affinity laws. Something I've used a lot over the years to explain one of the big benefits. And the affinity laws show the benefit of using variable speed. And as you can see, flow is directly proportional to the speed. Pressure or head is proportional to the square of the speed, and power is proportional to the cube of the speed. Now the power is the one that's really interesting for me in these when talking about variable torque applications, because as you turn the speed down, the difference is cubed, so the amount of energy you save is quite drastic compared to if you don't use a drive or you don't turn the speed down, or compared to maybe a constant torque application where you only get the savings of the percentage turn down that you apply. So with a variable torque application, the power, also known as Cube's law, is very important and something that's really useful. So the next one is oversizing. Oversizing happens quite a lot when equipment is sized early on in the project. So you might have a 7.5 kilowatt duty for an application. A contingency factor sometimes could be added in by an equipment designer or an OEM who've got the next best fit, which will be maybe a certain percentage. It could be up to 8.25 kilowatts. Then a further 10% may be added from a project engineer. Sometimes they do it for further expansion, sometimes they do it as a kind of cover factor. Once you've added all that, the next available motor frame size is 11 kilowatt. So you're at least a size above where you would usually be. And if you don't use variable speed to control that motor and turn it down, then there's usually huge opportunities for energy saving.
So how much energy can we actually save? Looking at the curve here that we've got on, as you can see on the left, we've got the power and the torque and the speed across the bottom. And as we discussed in the last section, due to these applications mostly always being oversized, there's always a chance for a reduction. And as you can see, from just a small reduction of 7%, which equates, to 3.5 hertz, results in a 20% energy saving. So it's quite substantial. So in frequency terms, that's going from 50 to 45 hertz. So that's quite a small reduction that produces quite a high energy saving. What are the potential opportunities on site? What should we be looking at and what should we be looking for?
So what are the potential opportunities on site and what do they look like? So a lot of times in the past, most motors were controlled direct online, stroke across the line, or maybe even star delta, as you can see in the picture there as well. So basically these motors are running at full speed and there's no speed control at all. The only speed control that would be applied would be some kind of mechanical speed control, or sometimes we have on-off where a motor would turn on and off multiple times to try and get the correct flow or speed that they were looking for. The other ones that you see is you might see an old drive already installed on an application controlling an older motor, maybe an IE1 to an IE3 motor. So if you see that, then there's potential for upgrade, as we'll see as we go through this presentation. I'm going to give some good examples on that. You'll also see drives controlling a new motor as well. So it might be a relatively new motor with a newish drive as well. What I would say, it's always important to look at these as well with your customers and with your end users to see how they're commissioned and see if they're set up correctly. Because a lot of times we've come across on site where they might have some newer equipment, but if it's not commissioned quite right, then they're not getting the best out of it. It might not get you a sale at the end of the day, but it's going to help the customer save energy and save carbon, which is, what we're about, what we'll try to do. And you're building that relationship with the customer as well in terms of improving that. As you can see, the IE3 to IE5, what I would class as newer motors, I'd say IE3 is probably the crossover point round about the middle, and we'll see a bit more of that on the EcoDesign slide. But IE5 to IE6 is where the motors are pushing now for the highest efficiency.
How to use the ABB EnergySave calculator. So this next section we're going to run through this software and how to use it. So let's take a look at the EnergySave calculator. I'll just run you through the interface and the options on the opening screen. So you can change the language in the top right corner, as you can see there. You can also change the currency as well. So I'm going to change this to British pound because that's what I'm going to use for this example. So I've got a lot of reference pricing and stuff which I can use. You can also change between metric and imperial as well. Moving further down the page, we've got applications you can select. So we've got fans, pumps or compressors. So you can select whichever application it is you're looking at. For this example, we're going to look at a fan and the different options available to us when fitting a drive. So as we look at this, on the left you can select basic or advanced. Usually I generally tend to stick to the basic one because that's pretty much enough for what we need when you're just showing a basic payback for somebody. The next option it's going to ask you is flow control. So how is it currently controlled? So you've got options: is it an outlet damper, inlet box damper, inlet vanes, no flow control at all, cycling on or off, slip coupling, 2-speed motor or voltage control. Some of the one I see commonly is cycling on and off. So I'm going to use this for this example, but you could use whichever one applies to your application. The motor power that we're looking at is 15 kilowatt. So you just enter the nameplate power rating of the motor that you're looking at for this application. So the next one is the motor efficiency class. So you've got all the options in here. If you've got something really old from the 60s, 70s or 80s, you can select those, which will give some reference data. More realistically, I'm going to select IE2 as a reference more to what we're looking at. As we scroll further down the page, the next one is the type of fan. So centrifugal or axial. The most common that we see is centrifugal, even though axial are coming more back into the market now, and we're seeing OEMs developing the axial fan offering as they can prove efficient as well. The next one you want to select is impeller type. So the most common ones we see in HVAC at least are forward curve blades. You can see backward curve and radial as well in different applications, but the most common one we see in HVAC is forward, so I'm going to stick with that. Next, we're going to look at the annual running time. So the hours for a full year, 24/7 are 8,760. Usually for a full year, I go with 8,000 hours. This is to allow some hours for downtime and maintenance, to give us a little bit more up our sleeve in terms of we're not promising too much in terms of saving. As we scroll down to the next, we're looking at the duration curve. So basically, what type of curve you're going to apply, control curve you're going to apply to the system when the drive's fitted. So the 3 options here which I'm going to show you, you've got the bell curve, which is one you would select if you're not sure, which kind of spreads across the operating cycle, across the flow percentages, so it's kind of hedging things a little bit. You've got PID, which obviously if you're looking to fit an airflow sensor or pressure sensor somewhere and you can operate off that, it's going to be the most accurate control and you're going to see the most savings. And the last one is 80% flow, which is a specific turn down. So a lot of times when I've seen people apply drives to old applications, they'll have a specific turn down of 20%, which is like going from 50 Hz to 40 Hz. And that'll give you good savings on its own. The other options are a bit more beneficial because you're gonna see greater savings, but sometimes it takes a little bit more work. So it's a balance between those two. For this, I'm going to stick with 80% flow because that's the least energy saving, so we can see the example based on that. The next thing that we need to enter is the economic data, which is the energy price. So you need to know the energy price per kilowatt hour of the customer, or you can give a guide figure. At the moment, in the UK at least, I've seen various different prices from 10 all the way up to mid-30s, 40p. Energy prices have been all over the place recently in previous years. So I've gone with 20 pence, which is round about the average, what I'm seeing at the moment. So once you put all that data in, you can see on the right hand side there, it actually shows you the different options and savings that we've got. So we've got with ABB drive control and without ABB drive control shown on the graph, and it's showing you the energy consumption on the left and the flow percentage on the right. As we've selected the 80% flow, you can see they're both stuck on 80% flow. As you can see with the drive, it's a lot less energy consumption, 64.1 compared to 96.6 megawatt hours. So below it shows you the results. 32.5 megawatt hours annual energy saving, 96.6 would be the annual energy consumption with the existing control method. The annual energy consumption with ABB drive control is 64.1, so as you can see there, you just take 64 from 96 and you'll get 32.5. Annual energy savings percentage, 33.6, quite high. So if you do find any applications where there is no drive installed and you can apply a drive and apply that turn down, as we mentioned earlier in the affinity laws and showing you the fan curve, the savings can be quite drastic just by turning down a small percentage. The annual energy savings, as you can see there, 6,501, which is quite a reasonable amount. If you've got the purchase price and the selling price in your local territory of the drive, you can obviously calculate a payback quite easily. Also, the CO2 reduction shown there, 9.8 tonnes a year. Something that we're seeing is also a target for a lot of people installing these. They're being targeted on CO2 reduction as well. So that's something that's quite important. So the next step we're going to do is click preview the report in the top right hand corner, because you can generate this into a short one-page report. And something I filled in earlier, you can put in the title, you can put the title of the site or whichever title you would like. And you can also put additional details. So I put London Theatre and Auditorium Air Handling Unit. As you can see, I'll add this to the actual report itself. And you can check on the left pretty much the detail that we've gone through. It's also got the input settings there listed at the bottom, so it gives you a good summary of everything. Once you've done that, you can actually click the download button there to PDF or CSV. So if you click PDF, it should load and it will open into a PDF and it'll look something like this. So this is something you can provide to a customer to show them exactly what you're proposing and give them an idea of the potential savings. EcoDesign directive. So let's discuss what that is and understand the detail behind what the directive is calling for. So let's look through the EcoDesign directive, which applies to upgrades to existing equipment, and it sets the scene nicely for the next tool that we're going to take a look at, which is the EcoDesign tool. So the EcoDesign directive was brought in 2009, and it was to set minimum efficiency standards for equipment to be installed. So we look at June 2011 there, stage 1, motors must be IE2 compliant. Then it moved 1st of January 2015 to stage 2, where motors rated with an output of 7.5 to 375 kilowatt must be either IE3 compliant, direct online, or IE2 compliant if fitted with a variable speed drive. It moved on in a couple of years later in January 2017 to motors with a rated output of 0.75 to 375 kilowatt must be either IE3 compliant, driven direct online, or IE2 compliant. So they increased the power band there. It was then adopted further in 2019 and The next regulation step was released in July the 1st, 2021, and motors with a rated output of 0.75 to 1000 kilowatt must be IE3 compliant. The option of IE2 with the drive is no longer available. Motors rated below 0.75 must be IE2 compliant. As you can see on that graph there, the first graph at the bottom with the shading. So this also started as well to incorporate drives. So drives rated from 0.12 kilowatt to 1000 kilowatt must be IE2 compliant as well. So this is something you can check in the EcoDesign tool, and we publish this data for our drives. And as you can see in that middle graph there, it's showing IE2 for all the drives. The next step in July 1st, 2023 was motors rated from 75 kilowatt to 200 kilowatt must be IE4 compliant. And some also motors, EX motors as well, must be IE2 compliant. The drives no changes from step 1, but this is just showing you the minimum efficiency is being raised across the board for installations. And we're going to see some of this in the EcoDesign and the benefit of upgrading from, say, an IE2 motor to an IE5, which we've got now, which can show you the efficiency benefits. So next is the ABB EcoDesign tool. This helps us meet some of the criteria set out in the ABB EcoDesign directive, which we discussed in the last section. I'm going to run through the tool and show you how to use it and how to get the best out of it. So the next tool we're going to take a look at is the ABB EcoDesign tool. And I'm going to use it to basically demonstrate the savings that can be made by upgrading a drive and motor power drive system from an IE2 rating to something like an IE5. So let's look at the tool setup and how it's laid out to start with. Similar to the EnergySave calculator, at the top right you can change the settings. Mainly under the language is set to IEC and metric. There's no option to do NEMA at this stage. If you just scroll down, we've got 3 options to select from. You can select complete drive module, so you can basically check the efficiency of the drive itself at different operating points. So the drive at full load, the drive at part load, you can set your user load defined points, and there's also a set of points that are used across industry in conjunction with this standard 61800-9-2 2023. So you can check the drive itself. As we mentioned earlier on the EcoDesign directive, the drives need to be IE2 standard efficiency or above. So that's something that's a requirement now. Moving on to the motor, you can do the motor itself as well. So you can check the motor efficiency at different load points, which basically gives you the power losses across the different load points. You can again do user defined points. The one that we're going to look at is power drive system, because we want to take a look at the system efficiency of the drive and motor together. And this is important because a lot of time you see when people look at these kind of things, they might look at a certain individual piece of the system and say, oh, it's 98% efficient, for example. But you've got to look at the system, and you've also got to look at what the operating point, what it's operating at. For example, we've all bought cars and we've seen the efficiency listed in the manual, and that's obviously tested in factory conditions in best case scenario, but in reality we never use it that way. Once you get it home and start driving it around, you'll notice that nobody gets the efficiency that's stated. It's never realistic. So that's why we calculate the efficiency of the system itself at the operating point. So if you click Power Drive System, it'll take us through to a selection. Filled in the selection already before because I'm going to do an example and compare between the two. So you've got an option at the top to start with the motor selection. You can either select an ABB specific motor or a non-ABB motor. In this instance, I've selected a non-ABB motor and I've picked a reference motor, so we can look at some reference data for a specific motor type. I've selected power at 15 kilowatt, so again you can select the kilowatt rating, whatever it may be. Speed, I've put 1500, which will be a 4-pole motor, which is what we see mostly in HVAC. You do sometimes see some different speed motors as well, which you can select as required. I've selected IE2 because that is the minimum standard which we should be seeing. You still might see the odd IE1 in real old applications and installations, but mostly you're going to see IE2 as a minimum now, I would say, in most cases. Network voltage, I've put 400. That's just general what we tend to go with, especially in Europe. Obviously, each area will be slightly different. As you scroll down, you can use the reference percentage losses as per the motor loss data. You can put it into watts as well. If you click this button, you can see it in watts. So on the right hand side, it shows you the results, and I'll go through these once we've fully selected. So at this stage, we'll click next. And for this part of it, this is where you get to the middle and you're selecting the drive. So, which is this CDM, how it's referred to in the standard. So for this, I've selected ABB drive. You can also select non-ABB drive as well. Frequency 50 or 60 Hertz, we're going with 50. So we're looking at an example for Europe. ABB drive family. Naturally, I've selected ACH 580. Best one in my opinion. Next, mains voltage 380 to 480. And then drive rating. See, the good thing about drive rating, it's giving you the recommended rating for the motor we've selected. As you can see there, it's suggesting the 33 amp drive. So as you can see on the right, the motor's 28.5, so that covers the current rating, and that's a 15 kilowatt drive as well, so the power is covered. You can also select protection class, whether you want IP21, IP55 or IP66. I'm going to leave this as IP21. So once you've done that, you can click select drive, and then it'll populate the data on the right hand side. And it also gives you the details of the drive in this box. So we click next. So next you can pick user-defined load points. So this is interesting because you can actually see the load point of what the drive's operating at now. If there's an existing drive controlling the motor. So we can give them more accuracy by actually using the load point that it's at rather than just full load and using the catalogue data. So what we're going to do is I've set the actual speed to 80%, and in a variable torque application at around 80% speed, the electric motor torque is going to be significantly less than full load, typically around 64% due to the square the speed relationship which we talked about earlier in the affinity laws. So if you reduce the speed, for example, by 20%, the required torque decreases by approximately 40% of that speed. If you go back and look at the curve that we had earlier with the torque and the speed, if you look at 80, it'll drop around 64 on the torque. So we can check that later as well. So once we've done that, we can now check to the right hand side and look at the results. So if you look at the top, we've got the motor data listed. So it's a reference motor, IE2, 15 kilowatt, 400 volts, 1500 RPM speed, current 28.5 amp. The drive, which we had some guidance selecting using the selection tool, ACH 580-01-33 amp-4. Got more details there, voltage, range, power, current rating and frequency. It's also giving us now power drive system IES class. So this is the efficiency class for the power drive system itself, and it's giving us an 86.6% efficiency for the system. It's also giving you the losses there to show you basically where it actually drops on that scale. So the next part, which is really interesting, the PDS absolute losses and efficiency operating points. So this is the power drive system, which is what we're interested in. It's got all the points listed, the standard points in blue, as you can see there, which are the points in the IEC standard, which I mentioned earlier. It's also got the gold dot listed there, which is our user-defined point, 80% speed and 64% torque. And it's giving us the efficiency of the package at that exact point, which is 86.2. Also at the bottom, you've got a table listing all the losses and relative losses and efficiencies at all these different points, should you need to know any details on any of these points as well. So the next button we're going to click is Preview Report. Once you click Preview Report, similar to the actual EnergySave calculator, you can create the tool, the actual report from the tool, and fill in the details, and it'll actually populate it into the report itself. The cool thing about this is it's got everything listed. So it's got your power drive system itself, which is what we're interested in for this exercise we're doing, because we're trying to demonstrate energy savings with different packages. You've also got your individual drive efficiency and the motor efficiency as well, should the customer be interested in that information. The information we went through earlier with the loss data is in there as well. You've also got the efficiency at all the different operating points, and you've got the table data as well with all those different items listed. We've also got a user-defined load point there as well. Further down, we've got the reference motor selected, the drive details, the drive technical data. So I won't dwell on too much. This is all stuff pulled from their catalogue. And it's also got explanations about how the PDS loss determination has been done, which is using the single loss determination method in accordance to IEC 61800 standard, as we mentioned earlier. We've also got different details there on all the parameters involved in that and the motor loss as well. So you can see there's a lot of data in there. It's quite a comprehensive report, and like the last one, you can click the button to turn it into a PDF to save and provide this to the customer. I'd always recommend as well with any report, when it comes to energy saving or stuff with data like this, I'd recommend arranging a call to discuss this and go through it with the customer to explain the details, because sometimes if you send reports like this and the customer reads it without you talking through it, sometimes they can interpret things slightly differently. So it's always good to actually talk them through the detail within this, so it's understood and they've interpreted the data correctly. So now I'm going to use the EcoDesign tool again to go through a different power drive system based with an IE5 motor. So I'm not going to go through and explain everything like last time, and we can just go straight to power drive system and click into that. And I've started this one from scratch so I can show you how the data populates and how it all comes together. So I'm going with the non-ABB motor selected there. We're going with reference motor as per the last one. So the power is 15 kilowatt. If you remember, the speed's 1500 RPM. So for this one, we're going to go IE class IE5, because we're going to look at upgrading it to a more efficient motor, and after we've done both these, we're going to look at the comparison between the two. So network voltage 400, we'll keep that the same. As seen last time, you can look at the reference motor losses. So what you need to do next is click the button there, select motor, and what happens is this top right is populated, the motor data is filled in there. Then we need to click next to move on to the drive. As you can see there across the top as well, it shows you the progress along the PDS, what you're looking at. So now we're into the drive. So next we're going to look at frequency. I'm going to keep that to 50. We're going to scroll down to ACH 580-01 as we mentioned, voltage 380 to 480, and drive rating also gives you that recommendation again of 33 amp drive. Protection class we're going to keep as IP21 as before. I'm going to click select drive. So what happens then, it will load the data and pull that through. And once it's loaded, you can see the actual data for the drive is pulled in there as well. Once you've done that, again similar, it pulls in the drive data at the bottom, but you can click next. So now we're going to add that same custom point that we had before, where the speed was 80% and the torque was 64%. So once you've filled those in, it should add this to the data on the right hand side. So as before, we've got the motor data at the top there. It should be pretty similar to the last one, slightly different current rating. drive, same as the last one. You can notice the difference there straight away. Power drive system, this is IES class 5. So the last one was IES class 2. You could see the last one dropped in the orange band, which showed the relative losses as IES 2, whereas this one's in the green band, less losses means IES 5. Looking at the next graph, the PDS absolute losses and efficiency operating points. As before, it's got the same standard operating points with the efficiency at those points for this package. Next, it's got the user defined point in gold, which is the one we're really interested in. As you can see, 91.5 and absolute losses less than before. So the last one was around 86%. This is one around 91.5. So you can see there's around a 5.5% increase overall. So that's something that's really standing out straight away. You also got the same predefined points before in the table. You've got your user load point at the bottom. If you click the same preview report, again you'll get the same data coming out. So you can fill your titling and all the rest of it. And as we can see down the middle, it's got the individual data as per before. And as you would expect, it's showing better efficiency across the board really. The drive will be similar, but the system itself is more and the motor is more, which are obviously very important. And also the PDS losses. So it's got all the same data in the report as well, which as you scroll down, I won't go through it all again, but it's like for like as the last one. And next we're going to move on to showing a comparison between these two.
So let's look at the power drive system package comparison between the IE2 one we looked at and the IE5 in terms of the motor. So on the left hand side we've got the system with the IE2 motor, and on the right hand side we've got the one with the IE5. Now the first thing you may notice is the drive module itself on both sides is identical in terms of the numbers, which should be because it's operating at the same frequency, same speed, so it should be doing the same amount of work. If you look at the motor on the left, the IE2 motor, it's showing you 89.4% efficiency on its own. If you look at the difference on the right hand side, the IE5 motor 94.4. So that's where our biggest percentage difference is. On here, it's around a 5% saving in the actual motor itself. And the really interesting one we want to look at is the power drive system on each. And as you can see on this one there, the power drive system is rated as IES3. Relative loss is 14%. And you can see the efficiency is running at 86.6%. If we move to the one with the IE5 motor, you can see the relative losses are less, almost 6%. Absolute losses are less, which you would expect. And as you can see, the power drive system efficiency is different as well. So 91.7 compared to 86.6. So this is just how you interpret the data that comes out from the tool on the different, when you generate the report at the end. Next, we're going to move on to a executive summary in terms of different costs and some real figures. So let's look at a comparison between the two motors. I've put together an Excel sheet to look at the energy cost comparison. At the top there, we've got a calculation to work out the motor power input at 80%. So we've got 0.8 to the power of 3, which is the inverse of the cube, which gives us 0.512. Times that by the motor power, and we've got our motor power at 80%. In the next section down, we've got the actual motor's efficiency. So you can see IE2 on the top there, and then IE5 on the bottom, multiplied by the operating hours, and that gives you the energy consumption for each motor. You can see the IE5 is less than the IE2, which is what we would expect. Moving on to the energy consumption and cost, so we can actually multiply that by the cost per kilowatt hour to find out the yearly operating costs. Now, I've used 20p as the energy cost per kilowatt hour, based on a rough average, what we see in the UK at the moment. This could vary country to country, which will obviously change the result. As you can see there, you're looking around £800 per year less operating cost for the motor, just by changing to a more efficient motor. Energy saving percentage of just under 6%, and over 4,000 kilowatt hours saved, and over 900 kilograms of CO2 saved as well. So there's quite a difference there just by upgrading the motor, which is quite impressive.
So let's take a look at a summary, and I've got 4 key points really that I want you to take away from this presentation. And the first one is using a drive can save energy even with just a small change. Now, a lot of times you may have customers with existing installations who are slightly nervous about changing things, if it's not broken, don't fix it, all that kind of thing. And they may claim that they need the current speed they've got, they don't want to slow anything down, but even with a small change in the system, in the speed, can result in substantial energy savings. As we've seen in the earlier slides, just a 3.5 hertz reduction, 7.7% reduction in speed basically, can save up to 20% of the energy, which is quite a lot. I think such a small reduction in speed wouldn't be that noticeable, and we've seen applications before where people have reduced it by that and they didn't really notice much difference in the performance of the application. The second point is the multiple types of opportunity for savings and higher efficiency. So it's not just about applying a drive to a direct online motor that doesn't currently have speed control or is controlled mechanically. It's also looking at the package as well in the system. So how is the system operating at the moment? What's the philosophy? Is there something more advanced or a better way of control or a better way of actually executing how the system operates that can improve the efficiency? And also, what about the motor as well? Even just upgrading the motor from a lower efficiency to a higher IU5 or above efficiency can make substantial savings itself as well, even if there's already a drive installed. So it's worth looking at that. And as we've seen with the EcoDesign tool, that gives you the benefit of being able to do that. So point 3 is use the ABB tools to help. So the two tools that we've gone through today, the EnergySave calculator is very useful for applying a drive to a motor that doesn't currently have speed control or is controlled mechanically. And as I just touched upon the EcoDesign tool, this can give you efficiencies at certain operating points, and you can compare efficiency between two efficiencies types of motors as well. So if you're upgrading the motor, it can give you an idea of energy savings for that. And the fourth point is really important, is demonstrate the savings for customers. So go to site, visit this and see the applications and understand how it operates and get as much detail as you can so you can explain to the customer why we can save energy and how they can save energy and try and take them on that journey together. It does help, and I think it makes them a lot more confident if you do actually visit and discuss the specific applications that they've got and come up with some examples, and the tools can help you do that. So thanks for watching this presentation on ABB Energy Tools. There's a lot of useful stuff in there that's you can demonstrate for customers, and you can actually show the savings, which I think it's okay telling people we can do something, but if we can put some numbers in front of them and give them some data, I think it means it's much more likely that they're going to proceed and potentially look at installing this kind of thing in the future. Thank you.